Hello everyone, this is Dr. Webb. In this calculus video, we're going to be taking a brief sojourn back to the land of the limits. And we're going to learn a neat little trick that's going to allow us to evaluate some pretty difficult limits that we weren't able to do before. So let's just hop right into it. So this trick is called L'Hopital's rule. I know it's spelled El Hospital, but it's pronounced L'Hopital. And he was a French mathematician. And so what L'Hopital's rule says is it says that suppose that f of x and g of x are both differentiable functions, where as they go to a, they either both go to 0 or they both go to plus or minus infinity. Then if you want to take the limit of f of x over g of x, you can do this by actually taking the limit of the derivative of f divided by the derivative of g, so long as the second limit exists or is infinite. And so a couple of things to note in this. We have this limit as x is going to a. This a can either be a real number or plus and minus infinity. So this is real or plus or minus infinity. And so it doesn't really matter. All the types of limits that we would want to do, we can do with using this rule. And if you think about, say if f of x and g of x are both going to 0, then, you can't just use that f and g are continuous to evaluate this limit, because you get 0 divided by 0, which doesn't really make sense. And so this limit is going to allow us now, this rule is going to allow us to evaluate an awful lot more limits than we were able to before. And so these limits, these 0 over 0 or infinity over infinity, these are types of what are called indeterminate form limits. And so these are indeterminate forms really means you can't just look at it and reason out what it has to go to. You have to do something a little bit more precise, or really in particular, it's a ratio where just using continuity, using that what values they're going to, isn't enough to tell you the value of the limit. You're going to have to use something else. Okay, and so let's start off looking at an example which we had already looked at before. So we already looked at how to get the limit of sine of x over x as x goes to 0. But when we did this before, so this was before we were figuring out what the derivative of sine and cosine are, we actually had to come up with this, a little bit intricate geometric argument where, this limit pops out by looking at comparing areas of triangles and sectors of circles and such and such and such. But now with L'Hopital's rule, we can evaluate this just by using the derivatives, which we now know. So first thing to note, as x goes to 0, sine of x goes to 0 and x goes to 0 as well. So this is a 0 over 0 indeterminate form. And so this is something that L'Hopital's rule definitely applies to. And so if we're looking at this limit, and we're going to apply L'Hopital's, so I'm going to put a note here saying we're doing L'Hopital's right here, and I'm just going to shorten it to LHOP. Then what L'Hopital's rule says is you take the derivative of the top, and so the derivative of sine is cosine. Replace it there. On the bottom, you plug in the derivative of the bottom, which is 1. And so now we have a new limit. Limit as x goes to 0 of cosine of x divided by 1. Now, this is something which is continuous at 1 now. This is just the limit of cosine as we go to 0. And cosine of 0 is 1. And so our limit is just 1. Now, one thing to note when we're taking the derivative for L'Hopital's rule, we're not using the quotient rule. Even though we have a fraction here, we're not using the quotient rule. L'Hopital's rule is very much different than the quotient rule. We're just taking the derivative of the top by itself separately and then dividing by the derivative of the bottom by itself separately. Totally unlike the quotient rule. So why does this work? So what's going on for L'Hopital's rule? I'm not going to give you the full proof because there's actually a bunch of different cases depending on whether the limit goes to 0 or infinity, depending on whether a is a real number or is plus or minus infinity. I'm just going to focus in on one case. And the case I'm going to focus in on is if a is a real number and both f of a and g of a equals 0. So this means that the limit, that we're thinking about these as being continuous functions, differentiable functions. And so this is saying that the limit, this right here is saying that the limit as x goes to a of f of x and g of x are both 0. And so we'll work out this case. This is actually the simplest case, but you get a feel on why this is true, and you can kind of go from here and figure out the other ones if you'd like to. Okay. So we're thinking about the limit of f of x over g of x as x goes to a, and so this is of the form 0 over 0 as an indeterminate form. And so the important thing to note is that f of a and g of a are both equal to 0. And so I can subtract 0 off from the top and the bottom, and that's not changing anything. But this 0 is meaningful here because that 0 really I can think of as being f of a, and that 0 I can really think about as being g of a. Okay, and so I can think about this as the limit as x goes to a of f of x minus f of a divided by g of x minus g of a. Now, I want to make this look like the derivative in some way. And so what I'm going to do is multiply the top and bottom by 1 divided by x minus a. And so, because I'm multiplying it to the top and bottom, really I'm multiplying by 1 here. And because we're taking the limit as x goes to a, we're not actually at a, we don't have to worry about dividing by 0 here. And so then when we fit this together, we've got the limit as x goes to a of f of x minus 0 divided by x minus a, and g of x minus 0 divided by x minus a. And remember that this 0, this is really f of a, and this 0 is really g of a. So what do we really have going on here now? Well, the top is the limit definition for the derivative as x goes to a, and the bottom is the limit definition of the derivative for g of a as x goes to a. And so this limit as x goes to a, the top overall is going to f prime of a, the bottom's going to g prime of a, and that's why we're allowed to replace the top and the bottom with f prime and g prime, right? Really, you can think about this fraction up top is getting closer and closer to the derivative. The fraction on the bottom is getting closer and closer to the derivative, and that's why it works. Okay, so we're going to finish this off with one more example. So we're looking at the limit of square root of x times natural log of x as x goes to 0 only from the right. And so as we go to the right, square root of x, that's going to 0. But natural log of x, as we go to 0 from the right, that's going to minus infinity, right? So square root of x is trying to send us, this is trying to make us really small. So wants to be really small, close to 0. However, on the other hand, natural log is going off to minus infinity, and so this wants to be really big and negative. So we have this tension here between these two functions where square root of x is trying to send this limit to 0, but natural log of x is trying to blow this up and take it off to minus infinity. And so this is really the idea of an indeterminate form. Just looking at this, I can't decide whether square root of x wanting to be small is going to win, or whether natural log of x trying to be really big and negative is going to win. And so this is a indeterminate form of the type, well, square root of x is trying to 0, but natural log of infinity is trying to go to, natural log of x is trying to go to plus or minus infinity. And so we'd say that this is a 0 times infinity type. Now, if you recall, for L'Hopital's rule, we need either 0 over 0 or infinity over infinity. L'Hopital's rule works specifically with ratios of functions. Right now we have a product of functions, and while it's an indeterminate form, it's not a ratio. And so how can we apply L'Hopital's rule here? Well, we're going to have to take this product and rewrite it as a ratio in some way. So we're going to, instead of multiplying by one of these functions, we're going to be dividing by its reciprocal. And so we have two choices. We can either move square root to the bottom, in which case we'd have natural log of x over 1 over square root of x. And so now we'd have minus infinity over infinity, so this is an infinity over infinity type. Or we can do square root of x divided by 1 over natural log of x. Okay, and so we have the choice of either one of these. And so this one on the bottom now, this is a 0 over 0 indeterminate form. And so the one that I'm going to do is going to involve which derivatives would I rather take, right? Natural log of x, taking the derivative of that is going to just be 1 over x. Taking the derivative of 1 over square root of x, that's just also going to be x to a power. On the other hand, for the bottom one, I'd be taking the derivative of 1 over natural log of x. And so that's going to pop in more powers of natural log in there. And I'm a little bit scared about having more powers of natural log. I'd rather have less powers. And so I am going to avoid the bottom one and focus on the top one. And so now I can apply L'Hopital's rule. And so the derivative of the top, derivative of natural log, is 1 over x. Derivative of the bottom, so this is really x to the minus 1/2. And so I'm going to get a minus 1 over 2. And then the derivative of x is going to get 1 less. And so right now it's x to the 1/2 on the bottom, so it's going to turn into x to the 3/2 on the bottom. And so now I've got fractions over fractions, and so I can rewrite this as the limit as x goes to 0. I'll pull the minus sign out, 1 over x, and then taking the reciprocal of the bottom is going to be 2 x to the 3/2. And so minus 1 over x times 2x to the 3/2. Simplifying that, I'm going to have a limit as x goes to 0 of minus 2 times just square root of x. And this, I have no problem plugging in 0 as we go to the right. And so this is going to be equal to 0, and we're done. Okay. If you tried to do this other one with the natural log on the bottom, what you'd find doing L'Hopital's rule is that you actually ended up with something worse than you had before. And that's all because of the natural log on the bottom. And so in that case, L'Hopital's rule doesn't work. And so with almost all of these, there's a good choice for which one to move on to the bottom, and there's a bad choice. And so usually you can tell if you've made the good choice is if after you apply L'Hopital's, you have something that's better than what you had before. And so we had square root of x, which we could actually evaluate. That's better than what we had before. If you had done the other one, you'd have more powers of natural log in there, and that would be worse than what you had before. And so that's telling you that you made a poor choice in rearranging it. That is all for this video, and I will see you again soon.